Okay, so let's actually pop up our presentation here. So it's always a cute little slide to start out with here. So we're going to end up looking at sorting. And we're going to look at it for a couple of different reasons. One of them is that it's going to give us some more practice with recursion. It's going to introduce some basic algorithms. I think the other thing that it also is going to do is that it's going to introduce us this whole idea of big O, which is going to give us an indication as to how complex a algorithm is. As the number of items that are involved in the algorithm, like sorting, as the number of them ends up going up, what happens to our resources? If we double the number of items that we're sorting, do we double the number of resources? Do we, is it squared the number of resources that we had? And we'll see that there's terms for this in big O, like a big O value of 1, a big O value of n, a big O value of log n or n log n, or that sort of thing. And we'll try to derive some of these values. So this is actually not all that long a presentation. There are two sorts that we're going to end up looking at. There's going to be a bubble sort and a merge sort. The bubble sort is a sort of a brute force sorting, where we just keep on sorting until there's no more sorting left to do. And the merge sort is a little bit elegant, where we end up breaking things up until we stitch things back together until we get two sorted lists, and then it becomes easy to sort those two sorted lists. So this is an example of a bubble sort, where it's going to be going through here. It's going to be comparing these two elements. It ends up switching them. And the reason why it's called a bubble sort is that you can see that the 6 is going to bubble all the way to the top. So we end up getting the, as if we move in this direction, we end up getting the, and I shouldn't say the 6. What I should say is that the biggest number is going to end up moving all the way to the top here. It bubbles all the way to the top. And at this point, we start the process again. So the algorithm is, I went through the loop of all the elements. Did anything change? If anything ended up changing, I'm going to go through it again, and I'm going to keep on doing it until nothing ends up changing. So let's actually just see how this ends up going. I just want to see if it ends up trying to do anything with the 8, because at this point, the 8 bubbled all the way up to the top, so you don't really have to consider it when you end up going through here. So bubble sort is, I think, pretty easy to visualize here. And again, you can see that the bigger numbers are bubbling up to the top. The little numbers eventually are going to end up bubbling down to the bottom, but it could take a while, right? If we had a really low number all the way on the right, we're not going to get it down to the bottom until the end. So the algorithm loop over the elements, swap anything that's out of order, and repeat until there aren't any swaps. Merge sort's a little different. And it's probably a little bit easier to visualize than it is to explain what's happening. But you can see you're breaking up this collection of elements into single lists, and then you end up patching them back together one at a time. So you take adjacent elements, 7 before the 8, 2 is before the 4, and now you have two lists, the 5 and 6 and the 1 and 3. The 1 is going to go first, the 3 goes second, and then we could just put these last two values back here. In this case, we end up getting the 2, now we get the 4, and then we could just have these other values go back. And this whole process ends up going on until here we've got these two sorted lists, so we've got things in order, and it becomes a lot easier to put them back together. Now, it's probably not apparent as to why this is so much more efficient, but we could actually even derive this eventually to see how this plays out. Now, I sort of hate when they end up doing these odd numbers here, but so here we've got these 7 elements that are here inside of an array. And so what we end up doing is we end up splitting this array in half. So this array ends up getting split in half. These other arrays end up getting split in half. And once now we have these, what it ends up coming down to is that the base case is that if I have a list with a length of 1, it's sorted. Okay, makes sense, right? So if I end up comparing 2 sorted lists, the same algorithm ends up happening where, again, I have a 2 sorted list here, a sorted list here. I can start with the 27, 27, and 38, right? I've got these 2 sorted lists here, 3 and 43, and so on and so forth. It gets, again, more interesting when you end up, sorting these larger lists where, you've got the 27 and the 38 and the 3 and the 43. And again, you look at the front of each list because they're in order, and you compare the 3 to the 27. So you use the 3, you compare the 43 to the 27, use the 27, you compare the 38 to the 43, and then you have the 38 and the 43. And so this is a much more efficient sort, and we'll explain why, and you'll be able to demonstrate why. So the logic here is to divide an array of n elements into n arrays of 1 element. And you end up merging neighboring arrays back together again. And you make sure when you end up merging them in sorted order. And you end up repeating until you're only left with 1 array. So if we talk about the merge sort, this is where the recursion ends up coming in. And again, this is a great way to sort of think about it. Take a base case, sort a list with 1 element in it. So we pass in that list with 1 element. We end up looking at the length. If the length is less than or equal to 1, great, we're sorted. Okay? So we wrote an algorithm that could end up sorting an element with 1 item in it. Now take an element with 2 items. Okay? We end up going in here with 2 items. We end up finding the midpoint of the array. And again, we end up doing that by looking at the length of the array. We end up dividing it by 2. We take the integer value, and we end up doing a splice so that we went in there with a 2-element array, and now we have 2 1-element arrays. We take those 2 1-element arrays, right? We have those 2 1-element arrays, and when we end up calling merge sort on this 1-element array, we go in here and we end up getting back this 1-element array here and a 1-element array here, right? We split it, and now we've got 2 sorted 1-element arrays, and then we write a function, which isn't shown here, which ends up basically looking at these 2 lists, and it just has to compare the first element of each list. If the first element on the left is less than the first element on the right, add the first element to the new list, shift it off the left list, okay? And keep on doing the same thing until one of the lists is empty. And when one of the lists is empty, you then can go and concat the remaining items on there. Again, it's 2 lists that are sorted together. So if it ends up working for an array of 2 items, again, recursively, it's going to end up working for an array of 3 items or 4 items or however many you're going to have on this list. So when you end up thinking about the bubble sort, you're thinking about looping and swapping. You're swapping items in position. When you think about a merge sort, you're stitching things up. Okay, you're separating things out into single elements and you're stitching them back together. Okay, until you end up getting bigger and bigger lists, and then you have two lists that you're left with, and those end up getting merged together. So let's go through, let's set this up. We're going to do the workshop. When we're done with the workshop, we're going to come back and talk a little bit about the complexity of sorting. Although frankly, let me just take a quick look and just see if that's the way it's set up on the schedule, or if it makes sense to just talk a little bit about the complexity now. Let's do that. We'll finish with the complexity. So when we talk about the complexity, there's two things that end up coming into play. What resources you need as a function of input size, right? I mean, it could be an efficient algorithm if there's 2 items, but how does it look if it's 2,000 items? Now, again, sometimes these things are linear, but more often than not, where you have things that are happening recursively, they can end up being fairly slow, or they can be expensive in terms of how much resources they take up. And sometimes there's an inverse relationship. So really what it comes down to is, what does an algorithm need to run? So sometimes it ends up needing space. Now, on the one hand, we could look at our bubble sort, really no space. We're swapping out items, right? There's no new arrays that have to get created. As opposed to when you start thinking about the merge sort, you could see that there's new arrays that you're creating as things end up getting merged together, right? You're merging other arrays. There's also time, right? How many operations does it take to do the algorithm? And that's sort of where this big O picture comes in. And usually for the big O, I think, well, I guess you could talk about it for space as well as time. But sort of, if you ended up finding out that the amount of operations that it took was, you could come up with a formula and say, hey, look, if there's n items, what you're going to end up getting is 5n squared plus 10. Well, first of all, you have a pretty expensive thing, right? I mean, if the, if things are expanding, if the time is exponential, right? Doubling the list is going to be 4 times the time that it takes. It's going to start getting pretty expensive. But the way that this ends up breaking down is that this becomes an O of n squared. You kind of forget about the 10 because it doesn't really mean that much. And the constants here, 5, end up going away. When we end up looking at the bubble sort, we find out that it's n squared. And the reason why it's n squared is that you're basically doing a loop, and it's something less than n squared, but you're looping through all the elements for all the elements, right? And you can see that. It keeps on going back and forth. The merge sort is less than that. And you could sort of, I was playing around with this to kind of derive, I couldn't find a good explanation of how it gets to be n log n. Go ahead.
So it keeps splitting it in half, right? So each time, I mean, for the case where you have an array of 1 elements, you don't have to do any comparisons. So that's kind of like, let's say nothing. So if you go 1 level up, you have the number of elements divided by 2 groupings, because each one is 2.
Right.
So that's the number of comparisons you do, 1 for each number of groups. When you go up 1 level from that, you have, let's say, 2 and 2 that you're comparing. So now there's the number of comparisons is still 2 for every 4 elements. There's 2 comparisons max that you have to do, right? Because when you compare the first 2, you push 1, and then you compare. Actually, I guess it could be 3.
I know. I had that same. I did the exact same. In fact, I did a video actually looking at the number of operations. Yeah, I think you're right. I mean, I think if we sort of think about it, right, and we could. I'm sorry for you guys at home. I want to actually draw something on the board, but we'll take a picture of it and show it. If we could maybe just think about how we could end up deriving that, maybe we could come sort of close. So, or I don't know. let me actually see something. Maybe we could even do it on a.
Each level you're doing on the order of n comparisons, and the number of levels is log 2 of that, because every time you're copying in half.
Right. Let's just see if we could take a look and see how we could sort of just show that. I know, I see what you're saying, but let's say, let me make this bigger. Let's try to do this. Let's say that we have 8 items. So again, I'm just going to put X's here. I don't know why I say again when I didn't say anything before. But 1, 2, 3, 4, 5, 6, 7, 8. Okay. So the first thing that we're going to end up doing for this algorithm is we're going to be separating these out into sets of 2. Okay. So 1, 2, 3, 4. 1, 2, 3, 4. So up here, I'll put what it took to get us down to this level. I would say that this is one operation, right? We just found the midpoint. That's really the only thing that we ended up doing here, allowed us to split it here. So what did this take us? This took us, we split twice. We go down here, we're going to find out that we're splitting once, twice, one, 2, 3, 4, 5, 6, 7, 8. So in order to get down to here, we've ended up splitting 4 times. Right? So now we've got our, we went from 4 to 2 to 1. And it's not coincidental, right, that that number is very close to n, right? 4 to 2 to 1, right? If you could imagine that we had, instead of 8, we had 16, right? I think we'd end up getting 15 or whatever it was, right? So this is going to be, to get us to there, it's something close to n. When we end up stitching these things back together, so here, we're going to have 1 group, 2 groups, 3 groups, 4 groups. Right, so we've got 1 extra group here. So I've got these 4 groups. So in this case, we ended up doing at most 4 more comparisons, right? And if we end up doing this again, we're going to have yeah, so here at the most, we're going to have, right, we could have 3 and 3. It's going to be 6, right?
Why 6?
Well, if you end up, I know, this just always kind of messes me up. The reason why it's 6 is that let's take this, it might not be 6, it might only be 2 from this list, right? If these 2 are lower than these 2, then it's only 2. But if this is lower, you know, and then we get this one, then we have to compare these 2. So we've got 3 from this side at most and 3 from this side. And this takes us down to, you know, this is 6. And if we end up going here, this is, you know, this is going to now be our final 8. And what do we have here? We had 3. At the most, we're going to have 7, right? Is that right? I think so. Yeah.
10 tops, yeah.
No, so I look, what it ends up coming down to here, I mean, exactly how this ends up getting derived is one thing, but we do know one thing. We know that the number of levels that we have here, that we're going to have to stitch up together, we know that that's going to be log n. Okay? Right? That's going to be the log of 8. You have 3 levels. And it's 3. How many times are we doing this? Again, if you end up looking at, I think initially when I looked at this, for some reason, I always was looking at it and thinking that I had like when I first looked at this, I kept on thinking that I only had 4 comparisons here, and I had 4 comparisons here, and I had 4 comparisons here. And in that case, it would be n over 2 times log n for the stitching back together. But you could see it's something greater than n over 2, right? It's something that's a, right. So we know it's a multiple of log n, but you're all, also, right, it's a number of, right, it's log n times something else, how many times we're doing this comparison. This, I think, starts to become somewhat meaningless when the numbers end up getting pretty big. So I don't know, I mean, it sort of will help you remember maybe that it's n log n, and there's probably some mathematical proof that you could end up doing to end up getting that exact number, although every time I look exactly how that gets derived, I don't quite understand the response. In any event, so this tells us about our complexity of our algorithm. There's also, an idea of space here. And again, the idea here is that you are going to have to create a new array when you end up using the merge sort. So there's some resources that are there. In the case of the bubble sort, there's no resources that have to end up getting taken up. And why is the merge sort faster? And again, you have this whole idea of the number of steps to actually go and string things back up together. Again, you're sort of doubling what you're connecting up every time. It's that idea you have those 3 steps for that, the stitching process that's going on. Okay. So I'm going to stop this screencast. I'm going to go in and I'm going to open up the sorting workshop, pair you guys up. Guys that are at home, you can work on your own. One of the things that I did with Antima was that I set up an account on Cloud9, and we were able to actually go in there and sort of work together on it. If you have some time, you could take a look at it. It wouldn't be a bad idea for people that want to work outside of class to have that kind of environment to set up in. And maybe I'll find one of you guys at home and set things up on Cloud9 and pick different people to sort of work through on this. But all right, I'm going to open this up, and we'll end up doing the workshop. The heck? All right.
Do we have access to that presentation?